Hello everyone, and thank you for joining me. Today I will discuss a line of our work on decoding quantum low density parity check or QLDPC codes. The central idea is quite simple. Belief propagation already gives us a low complexity local message passing decoder. Instead of replacing its update equations, we ask whether changing the order of those updates can make the decoder more reliable. We first study sequential belief propagation, where nodes are updated one at a time. We then use reinforcement learning to choose the update order from the syndrome information available during decoding. I will build the necessary background gradually, so no prior knowledge of quantum error correction is required. Before introducing the background, I want to place this presentation within our broader research program. The first work showed that sequential belief propagation can substantially improve the decoding of QLDPC codes compared with the conventional flooding schedule with much lower number of iterations. The second work, which is the main focus today, uses reinforcement learning to select the state-dependent order for those sequential updates. We then developed two extensions. In the cluster-based method, the agent selects a group of variable nodes and the nodes in that group are updated in parallel. This creates a useful trade-off between the performance of our sequential decoding and the latency of parallel decoding. In the other work, in the list-based method, we keep several promising decoding trajectories so that the decoder is not committed to only one local decision. Today I will explain the first two ideas in detail and use the later work mainly when discussing the numerical results. Here is the roadmap for the talk. I will begin with ordinary binary error correcting codes and syndrome decoding. That classical picture gives us the right intuition for the quantum case. Next, I will introduce qubits, Pauli operators, and stabilizer codes. I will then simplify the decoding problem to an independent Pauli-X channel where the error can be represented by binary vector. In that setting, I will review flooding belief propagation, sequential variable node scheduling, and our reinforcement learning formulation. After the main ideas are clear, I will extend the discussion to the depolarizing channel where X, Y, and Z errors must be handled jointly. I will finish with numerical results for several representative quantum LDPC codes. To begin with, let me start with a binary linear code. A length n code is a collection of binary vectors called code words. The word linear means that if I add any two code words modulo 2 like W and X, then the result is also a code word in the set C. We can represent our code with a generator matrix, call it G, is a K by N matrix, and its rows can generate all the code words, and the G maps our data bits, which is a length of K, to our code words that are lengths N. Or we can describe and represent our code using a parity-check matrix. A parity-check matrix is it's a binary matrix that has n minus k rows and n columns, and any code word x satisfies h times x equal to 0. Suppose a code word x is transmitted and an additive binary error z occurs. It means that our receiver observes y, which is x modulo 2 addition by the error vector z. Everything is of length n. And the syndrome we defined as h times y. Y is our received vector, but y we said that it's equal to the x plus z, and we said that h times x is 0. So the syndrome becomes equal to the h times z. Therefore, the syndrome depends only on the error pattern over a binary symmetric channel. Binary symmetric channel means that every bit that we transmit with probability, let's say p, which is the crossover probability of binary symmetric channel, flips. Every 0 becomes 1 with probability p and remains 0 with probability 1 minus p. Similarly for 1, it flips to 0 with probability p and remains 1 with probability 1 minus p. Now, the syndrome decoding can be viewed as finding an estimate z hat, an estimate of our error z, such that h z hat becomes s. In here, we said that for our actual error that happened, h times z is equal s. But in the syndrome decoding, our task is to find error vectors, an estimate of the error vector, that h times that estimate is equal to s. But remember, if you know h has n minus k rows, but n columns. So the number of rows is less than n, and our syndrome now is a vector of length n minus k, but vector z error is of length n. We have a vector with a smaller size, n minus k, but we want to find a vector of bigger size. From linear algebra, we can see that there are too many such error vectors. Actually, exponentially many of those error vectors that can give that syndrome. Ideally, we want our syndrome decoder finds the error vector that has the lowest weight. This becomes a maximum likelihood decoding. In classical coding, we use parity checks, H, to infer an unknown binary vector pattern, Z hat. Quantum coding keeps the same high-level idea of this syndrome decoding. It measures parity check-like constraints, that every bit of syndrome in the classical LDPC codes defines a constraint of the code words. So in the quantum also we measure parity check-like constraints, and we try to find the error vectors. We infer the error from the measured syndrome. In the quantum error correction, we cannot take a look at the qubits. In classical error correction, when we do the decoding, the majority of the decoders, they try to find the code word x, that x plus z is y. Rarely we see an actual practical decoder that tries to find the error vector. If we find the error vector, okay, and we have the receive vector y, we can sum the error vector with y and obtain x. But in the practical classical error correction, we go and find the x, and finding x, and x is a unique vector, and finding it is more practical. But in quantum error correction, we cannot take a look at the qubits. So we measure the syndrome, we find the syndrome, and we go and try to do the syndrome decoding. The main difference is that the error is now a Pauli error acting on qubits. In the classical error correction, when we have binary symmetric channel, the errors are just flipping the bits. But now in here, the errors are Pauli errors, act on qubits. So first we need to understand what is a qubit and what the Pauli operators, the equivalence to the errors, concept of the errors, what are they, and how they define quantum parity checks. A classical bit is either 0 or 1. The two basis states in the quantum error correction are cat 0, we read this notation as cat 0, and cat 1. Cat 0 is a binary vector of lengths 2, 1, 0, and the cat 1 is the binary vector of lengths 2, which is 0 and 1. You should remember these definitions. And in general, a qubit is a linear summation of cat 0 and cat 1. Cat psi, an arbitrary qubit, is alpha cat 0 plus beta cat 1. And this psi lies on the unit ball, the sphere of the unit ball. So we have this constraint. Every qubit has this constraint, alpha 2 plus beta 2 is equal to 1, such that alpha and beta are complex numbers. So from this we can say that cat psi is a vector of lengths 2. Each element is a complex number and we have this constraint on it. That is one qubit. What about multiple qubits? Multiple qubits describe using a tensor product. If you don't know what is tensor product, just pause and for a few minutes try to understand what is a tensor product. For example, when we have two qubits, let's say we have qubit cat A and qubit cat B. Each of them are, as I said, a vector of length 2. Now we have two qubits is the tensor product of them. For example, when we have cat 0 and cat 0, these two qubits, the two qubits that we have together, we can use this notation, cat 0, 0, or we need to write like this, cat 0, tensor product of cat 0, and if you tensor product them, we will get 1, 0, 0, 0. So with tensor producting of two qubits, we will get a vector of length 4. So cat 0, 0 is a tensor product of length 4. You can now with yourself like write on a paper what is cat 0, 1, what is cat 1, 0, and what is cat 1, 1. Cat 1, 1 is the vector of length 4, which is 0, 0, 0, 1. 1 in the last, 1 as a last element. In general, when we have n qubits, the state lives in psi 2, which is for one qubit, tensor power 2 n. So for 4 qubits, we will have each 4 qubit is a vector of length 16. 2 to the 4 is 16. Now, we understand what is a qubit, but what is the error that acts on a qubit? One qubit, I said that is a vector of length 2. So an error should be a matrix, 2 by 2 matrix, that can act on a qubit, which is a vector of length 2. The errors that we study are the identity matrix. It means that we don't have any error. If we multiply this with any vector 2, the result is that vector 2. X, they call it the bit flip error. Z, they call it the phase flip error. And Y, they call it the both X and Z error. They act on the basis states 0 and 1. Intuitively, X, as I said, is a bit flip, Z is a phase flip, and Y is both bit flip and phase flip. Let's see, for some examples, X times 0, X times cat 0, this is our matrix X, and this is cat 0. If we multiply, the result is 0, 1, which is the cat 1. X times cat 1, the result will become cat 0. That's why they call it x as the bit flip. X converts 0 to 1 and 1 to 0. And you should remember these four matrices. And if you go deep down to the quantum error correction, any error in some way, in some finite, maybe logarithmic finite, any error can be obtained from a sequence of these errors. So x swaps 0 to 1, and we call it bit flip operator. What about z operator? Z times 0, if you multiply the matrix z by 0, 0 stays 0, but z1, now it's minus cat1. So z does not swap 0 and 1. Instead, it changes the sign or phase of the cat1 component. That is why z is called a phase flip operator. For n qubits, I said that n qubits is a vector of length 2 to the n. For example, 3 qubits is a vector of 2 to the 3, which is 8. So an error should be 8 by 8 matrix. For n qubits, an operator, an error, acts on each qubit separately. For example, n qubit Pauli operator has the form P1 tensor product P2 tensor product up to Pn. Each of Pi's are one of those four matrices that in the previous slides I defined. So if we tensor product these 2 by 2 matrices, the result is 2 to the n by 2 to the n matrix. But we know that these are n Pauli operators, and if we have n qubits, the first Pauli operator acts on the first qubit. The second Pauli operator acts on the second qubit, and nth Pauli operator acts on the nth qubit. For example, when we have this 8 by 8 matrix, x tensor product I tensor product z, sometimes we can just write it xiz without writing tensor product. It's just a notation you can see in different papers. This means that the first qubit will be flipped. The second qubit has no error on it, and the third qubit, the phase will be flipped. It means that 0 remains 0 and 1, cat1 will become minus cat1. So these tensor product operators form the n-qubit Pauli group. If you don't know what is a group, meaning in the group theory or linear algebra, just search it up. Group, the elements of a group are close. It means that if we multiply two groups, the result is also a group member. They have distributive operation on it also. What does it mean if this is one in the 3 qubit Pauli operator? This is one element, and if we have another element like y tensor product x tensor product I, and we multiply this 8 by 8 matrix with the other 8 by 8 matrix, we will have new 8 by 8 matrix. And in the tensor product rule, the first Pauli operator multiplies with the first element of the other one. The second Pauli operator will be multiplied with the second element of the other one, and z with the other one. It's like this, how we have the operations. Let me go back to the definition of these four matrices, and if you multiply the identity matrix by itself, the result is identity matrix. If you multiply x by x, the result is identity matrix. Similarly, z times z is identity, and y times is identity. And if you remember, in here, I said that every qubit lies on the unit ball, the surface of the unit ball. And now if I multiply those matrices that lie on the unit ball, we need these operators to be unitary. It means that z times z should be identity. That's why if we multiply z by a qubit, the resulting qubit now again lies on the surface of the unit ball. We say that two operators A and B commute if A times B is B times A. The operator A, it can be one of those I, X, Y, Z, or the tensor products of them if we have n qubits. And we say that they commute if AB is equal to the BA. And we say they anti-commute if AB is equal minus BA. For example, if you multiply XZ and if you multiply Z by X matrices, you can say that they anti-commute. This matters. You should remember this. XZ and XZ is equal minus ZX. You should remember this. This is very important. This matters because stabilizer generators must commute with each other. I will clarify this more. A quantum stabilizer. Now, I assume that you know what does in linear error correction. I assume that you know what is a classical error correction. Now, in the quantum, when we want to find and define a code, a quantum stabilizer code is defined by a set of commuting Pauli operators. So I define what is, for n qubit, what is a Pauli operator, and I define what is commuting, and a stabilizer code is defined by a set of those commuting Pauli operators. This set forms an abelian subgroup. If they commute, and if they are group, now that they are subgroup and they are abelian subgroup, and we call them stabilizer group. Now, a code space is the set of states fixed by every stabilizer. So we say that cat psi, for example, this is our code word, cat psi is a code word if and only if we multiply m, our Pauli operator. For n qubit, it is n by n matrix. M times psi is cat psi for any element of this psi. This is the definition of the code space. And if you remember, I said that M is a unitary matrix. I said that each of those X, if we multiply them by each other, we will get the identity matrix. Now assume that we have this matrix, and if we multiply it by itself, it means that P1 times P1 is equal identity, P2 times P2 is identity, and P times Pn is identity. So overall, if we multiply this by itself, we will have identity matrix of size 2 to the n by 2 to the n. And from linear algebra, if you have a unitary matrix, its eigenvalues are either +1 or -1. If you remember from linear algebra, to find the eigenvalue and eigenvector, for example, we have a matrix A times V equal to the lambda times V. The lambda is our eigenvalue and the V is our eigenvector. In here, M times cat psi this vector cat psi, is equal 1 times cat psi. So the eigenvalue is 1 and the eigenvector is cat psi. So we say that a code word is the eigenvalue, eigenstate of the eigenvalue 1. And because M is a unitary matrix, these eigenvalues can be either 1 or minus 1. So we don't like the minus ones and we just like the plus 1 eigenvalues. And if you understand, cat psi is a vector of length n, and when we constrain it by a stabilizer, we reduce the eigenvectors are either, they are one vector for the eigenvalue 1 and they are one vector for the eigenvalue of minus 1. We discard those eigenvectors of minus 1 eigenvalues and we keep just those that are corresponding to the eigenvalue of 1. So we discard half of it. So for each element of this state, the generator matrix that generates its S, for each element of it, we discard half of the vectors. So if we have n minus k independent stabilizer generators, this is just linear algebra. The code now, for each of the vectors in the space of the n vectors, we discard half of it. So a vector of length n, the space is 2 to the n, and each time we discard half of it, so we divide it by 2, we divide it by 2, and we divide it by 2 to the n minus k. So now we will have 2 to the n over 2 to the n minus k. The result is a vector of a space 2 to the k. So we say that this code space encodes k logical qubits into n physical qubits. That is in the matrix notation, the Pauli operators. But we can map it and in the notation of binary format. Now, I won't go just now in the detail how we map it to the vectors of binary notation. In the next slide I will say, but let's assume that the stabilizers, the elements of the Pauli operators, the element of S, can be, each of them can be rows of H. So we will have, if we have n minus k independent stabilizers, so the matrix H has n minus k rows. Each row of H represents one stabilizer generator, and we have this constraint. Where does this constraint come? It comes from this one that we defined. Each x times z is equal minus z times x. And we only define the commuting Paulis. So we have this constraint. So we don't go to the design of the parity checks of the quantum LDPC codes. Our lecture today is on the decoding side. But if you want to design parity check matrices, we need to have these stabilizers. And we don't study such these general matrices. We go to a subclass of them, CSS codes. C comes from Calderbank. This is in the classical error correction, we have codes, but we mainly study the linear codes. Also for the quantum error correction, we don't study much the stabilizer codes. We study a subclass of them. The majority of the practical codes are CSS codes. So from now on, assume that we have just the parity check matrices of the CSS codes. In this notation, h of x is 0, G2, with G2 is a generator matrix of a classical error correcting code, and HZ is H1, Z. And this constraint now reduces to this constraint. So if you want to design CSS code, you need to define G2 and H1 such that we have this constraint. For conceptual clarity, from now on, for the majority of this lecture, I will assume that we only have X-only channels. It means that, as you remember, I said that we study the matrices I, X, Z, and Y. Now let's assume that the Z operator doesn't happen and Y doesn't happen, and only the X error happens. It means that either we have identity matrix as an error or the X metric as an error. So we can map it to a binary case. Whenever we have X error, we say that, when we map it to the binary error, we have 1 in the element of the binary vector error. And when we have the identity matrix error, identity operator, we say that we don't have an error in the binary, we show it by 0. So our error on the n qubits, we can conceptualize it as a vector E of length n, an element is either 1 or 0. And we can reduce it to H1, the CSS matrix, this one, and we define the syndrome of the X error, H1 times E, if H1 has M1 rows, Sx now has M1 elements, which M1 is n minus k, is the number of rows of H1. And the number of columns is n, which is we have n qubits. Now the problem becomes a syndrome decoding. As you remember in classical error correction, if we have H1 parity-check matrix, binary parity-check matrix, and if we have the syndromes Sx, which is a binary vector of length M1, our task is to find a matrix E hat and elements are of length n and elements of 0 or 1. Wherever we have 1, we understand that we have X operator. In a quantum code, different physical errors of length n can produce the same syndrome, as I explained also in the classical error correction. I said that this is of length m1, but E error is of length n, which is a bigger size. So exponentially many of these errors can produce the same syndrome. Unlike the classical error correction, that our task is to find the code word, which is unique, in here recovering the exact physical error is not always necessary. So we don't need to recover the exact error. And also, if we find an error vector, E hat, that satisfies the syndrome, means that H1 times E hat equal Sx. In that case, even we may not have correctly decoded and we still have a logical error. Thus, syndrome satisfaction is necessary but not always sufficient for successful quantum decoding. The performance measurement that we consider is frame error rate, which is the probability of either having logical error or decoder failure. To keep things simple in our training, we only trained up to the case that H1E had equal to Sx. It means that we want to find error vectors that are syndrome satisfied, and at the end for the evaluation we see that if we are having a logical error or not. To illustrate things by an example, consider this H1 matrix. It has 5 rows and 15 columns. Each column corresponds to a qubit and each row corresponds to a stabilizer, and it defines a constraint on the qubits. For IID X errors, we will have an X error with probability P of X over each of the qubits. To start the belief propagation decoding, we need the channel LLRs. We define it by mu v, which is equal log of 1 minus px over p of x, which is the probability of not having an error, not having an x error, over the probability of having an x error. And this is the corresponding Tanner graph. C1, which corresponds to the first row of the parity-check matrix, has 1 in the first position, has 1 in the second position, and has 1 in the third position, like this. It has 1 in the first, second, and third positions. Similarly, the row 6 has 1 in the third position, has 1 in the 8th position, has 1 in 9th position, and 12 and 13. Each variable node corresponds to a column. For example, the last column has 1 in the last row and has 1 in the fourth row. In the fourth row, this one has 1 in the fourth row and 1 in the last row. The initialization of the LLR, mu v1 up to mu v15, are all same and is obtained by this, which is the p of x is the probability of x error. And in the performances, when we plot, the vertical line is frame error rate and the horizontal line is p of x. For different p of x, we find the probability of having an error, not able being decoding to the right error vector. The Tanner graph, as I explained, has variable nodes for columns and check nodes for rows, and each edge is, we have an edge v to see if and only if that element of h1 is 1. It means that we have this one, the column 4 and row 2 is 1 because we have an edge between the V4 and C2. And given the measured syndrome, we have these syndromes measured, and from those ones we will find the error vector that corresponds to the variable nodes that satisfies h1 hat equal to sx. In my note, sometimes I show the error with e, and because it's x error, sometimes I show it by x and the estimation by hat. And as I explained, mu v, the initialization is like this. And when we are doing the BP decoding, BP propagates messages from the variable nodes to the check nodes, and I show it by this, m of v to the c, and from the messages that propagate from the check nodes to variable nodes by mc to the v. Each has its own formula that are studied a lot in decoding classical LDPC codes as well. In flooding BP, all nodes of the same type, means that all the variable nodes, they propagate messages together to all the connected check nodes, and then from all the check nodes, the messages propagate to all the connected variable nodes. And then we do the hard decision on the variable nodes and see if h times that hard decision is equal to the syndrome or not. This is one iteration of the flooding BP, or sometimes we call it parallel BP. And if the syndromes are satisfied, we can say that we can quit the decoding algorithm. If not, for some defined number of iterations, we do this iterative belief propagation decoding. For example, we can do maximum up to 100,000. It depends on how much latency we can tolerate. So one iteration, as I said, it's update of all check nodes to variable nodes and variable node to check nodes, then do the hard decision and then see the syndromes are satisfied or not. This schedule is simple and parallelizable because we are updating all of them together. But the problem is that whenever we have small loops in the Tanner graph, it means that from one variable node, for example V9, we go to a check node like C6, and we go to the, for example V12, we go to another check node, for example C2, and then we go back to the V9 that we started. This is a cycle 4. If in that case the same very similar messages will oscillate, will go back and forth between these two variable nodes. Sometimes the loop is, the length of the loop is 6. That one is also bad. And in the construction of LDPC code, designing parity check codes, in the classical LDPC code, we so rarely have a cycle of length 4, and the number of cycles of length 6 are very rare. But in the Tanner graphs of the quantum LDPC codes, especially when we have both X error and Z error, we will have lots and lots of cycle 4s. So having this flooding BP doesn't have that much good performance. This is the formula that we will have for propagating messages from check node to variable node. Let's go to the Tanner graph. For example, from C2, we want to send a message to V4. To do this, from the previous iteration, we collect message from V5 to C2 and V6 to C2, all the connected ones, except the one that we are sending. When we want to send message from C to V4, we don't consider that message we just received from V4 to C2. The other messages that we obtain from the other edges, we use them in the formula and send it to the V4. Similarly, if we want to send a message to V5, we just use the message that we got from V4 and V6. So in this formula, if we want to send message from check node C, and in that example C2 to V, in that example to V4, we consider all the variable nodes, all the messages that we obtained from the, this formula is it shows the set of all the variable nodes that are connected to the check node C, in our example C2. So all the variable nodes that are in neighbors of the C, except the V that we just received. We use those messages. In this formula, we multiply them together, then take a tangent hyperbolic and minus 1 to the syndromes of the corresponding to the check node, in our example C2. And we obtain this message. For variable node to check node, we sum all the messages that we obtain from the neighboring checks of that variable node, except from the check node that we want to send the message. We sum all of them together, plus the message that we initialized our LLR. I gave its formula in the previous slides. And this is the propagation of the messages between variable nodes and check node. Then, after doing one iteration, after doing each iteration, we need to find the hard decision of that variable node. To find the LLR of one variable node, we sum all the messages that are connected to that variable node. Mu v is the channel LLR, and this is from all the edges that are connected. We sum them up to get the LLR of that variable node, and if it is negative, we say that we will have an error on that variable node. It means that we will have an X error. If not, we say that we don't have an error, X error. Now we are only considering, as I said, the X error. And we will stop if this is the width element of the vector X. And if we consider this for all the variable nodes, then we multiply by H1. If the syndrome is satisfied, we stop the decoding. If not, we will repeat this for another iteration up until we have a syndrome satisfaction or we reach to the cap of the iteration that we are having. In flooding BP, all variable nodes update in one round use the same old information. It means that it uses the messages that we got from the previous iteration. In sequential BP, the one that now we are considering, nodes are updated one at a time. So later, for example, assume that we update node V2, and this node V2 is connected, for example, to check 5. And now it's the turn of updating node variable node 9. And also 9 is connected to C5. So again, it uses the messages that is coming from C5 or the variable nodes that are connected to it. This kind of using repeated kind of messages may inject asymmetry and solves the problem that we had, I said that for the loopy graphs, or make the convergence even faster. Two common sequential strategies are sequential check node scheduling. It means that we update the check nodes one by one, or the sequential variable node scheduling. In my paper that I introduced in the second page, I considered both of them, and both of them could be achieved to the better performance to the flooding BP with lower iteration. And here I assume that as an example, we are doing sequential variable node scheduling. For example, the first variable node that we update is V5. We propagate messages to the connected to check node and propagate it back. Then now it's time for the variable node 8, and we propagate messages to the connected check node. And then now the time is for the variable node 2. But notice that C5 is already updated by when we are updating V5. Now V2 uses the messages in here, or the V5 that just got updated. And this is the sequential decoding. But now someone may ask that how we know the order of updates. Why first V5, then V8, and then V2? In our first paper, we considered a random order of the variable nodes. At the first, we randomly chose some order and we stuck to it. But can we use RL or other optimizations for finding some optimal order or some better order? Yes, we used RL and we saw lots of improvement on the error correcting possibility. But may someone come up with another AI method, or even redefining the things that we are defining in our RL for example, defining the state, defining the score function. Each of these may improve the algorithm further. This is the training algorithm, how we train our RL, how we train the Q table. We use a Q table to do the RL. Let's go to the details of the algorithm. Our Q table, we initialize with 0, all the elements of the Q. Let's talk about the size of the Q table. Q table has n variable nodes for when we have n qubits. And the number of rows of the check nodes are defined by the maximum degree of the variable nodes. In this example, maximum degree of the variable nodes is 3. Some of them are 2, but the maximum is 3. For example, for V8 is connected to C3, C6, and C7. And after doing the message propagation and update, the syndromes, the 3 syndromes, are satisfied or not, so that they are 0 or 1. If 3 of them 0, so 0, 0, 0, we map it to 0. If 3 of them are 1, we map it to 7. If, for example, it's 0, 0, 1, we map it to 2. This is a map. We map a binary vector of length 2 to length 3 to a number between 0 and 7. So we will have 8 numbers. So the Q table has 8 rows. So the maximum degree of the variable nodes, if it is, for example, 6, 2 to the 6 is 64. So the numbers are from 0 to 63. So we will need to have a Q table of 64 rows. And in the training, we train for episode 1 to Emax. In all the simulations in our papers, I used Emax of 100,000, and then we need to map the probability of having an X error uniformly on a P-train is a set. In my simulations, I used P of X between 3% to 7%. Then now we need this is training, so we can know the E, our error vector, which is a Bernoulli. It means that each of the elements of E is 1 with probability P of X. And then we compute the syndrome. Then we set the mu X is the channel LLR. I think previously I used mu V notation, but I said that we may change the notation, and then initialize the E hat. We want to find an E hat, the algorithm. So at first we initialize it to 0, then we define the delta. This is the mismatch vector, is the summation of Sx, our syndrome, XOR by H1 E hat. At the beginning I said this part is 0, so delta is just Sx. And the number of ones of delta is the number of syndromes that are not satisfied. Then we do the BP for Imax iterations. In our training I use Imax of 100, but in the inference I use different Imaxes, 1,000 and 1,000. It depends on the simulations that I did. Remaining is the set of variable nodes that have not been updated yet, set of the index of the qubits that we have not updated yet. If we update, for example, V2, we exclude it now from the remaining. Then we update V5, then we update V1. One by one, we exclude it from remaining. Then for step 1, up to the remaining. At the beginning is that all the variable nodes that we update. Whenever we update it, we exclude it. If delta is 0, when delta is 0, if we find an error vector E hat, that H1 E hat is plus H1 E is equal delta. This is because this is binary. That one is 0. Delta is 0 when H1 E equals to the H1 E hat. It means that when E is equal E hat. Sorry, because it's not because E equals to the E hat. It's just because we have an XOR in here. It means that we only have a syndrome satisfaction. It means that H1 E hat is equal to the Sx. If it does happen, we break from the training that episode and we go to the next episode. For each variable node that we update, we find its syndrome. I explained how we obtain the state of that variable node. I explained how we obtain the state of the variable node. I said that if it's connected to 3 check nodes, and if they are 1, 1, 1, we map it to 7. Sigma I will become 7. If it is 0, 1, 1, we map it to 4. So sigma I is 4 in that case. And then we choose a variable node. This is the next variable node that we want to update from remaining by epsilon greedy. What does epsilon greedy means? It means that we'll take a look at the sigma I row of the Q. If sigma I is 4, we'll look at the 4th row of Q and find the maximum value of that, and we call it A, and this should be in the remaining set. Or from the remaining set, we pick something in random with probability epsilon. So with probability epsilon, we choose something from remaining in random and say it's the next variable node that we need to update. Or with probability 1 minus epsilon, we choose the maximum value of that row corresponding to the columns of the remaining. And in my simulations, I picked epsilon 0.6, and in each iteration, I reduce it until it becomes very small. W before is the number of ones of delta. It means that how many syndromes are not satisfied before the updating of that variable node, and then we do the message passing for that variable node, sequential variable node scheduling of that variable node. Then we check now how many syndromes are not satisfied. Then we obtain the score function RT. It's the difference between how many improvements we had, how many syndromes now are satisfied more, and we divide it to the degree of that variable node. For example, a variable node is connected to, for example, to 6 check nodes. This number can become between -6 and 6 and when we divide it by 6, it's now between -1 and 1. Someone can put an absolute value, make it between 0 and 1. It's just hardware implementation and doesn't most probably improve the performance. Then we, after obtaining the score, we remove that variable node from the remaining and then go to the next variable node that we got. Now we update the Q table. This is very similar how someone updates in any RL algorithm, and it's just a formula, and I won't go to the details of it, and just write the formula and update the Q table. So what we do, instead of picking the next variable node randomly, we learn it using the Q table. And in our RL, we call it RL, sequential variable node scheduling, or in my later papers I used RLS. The message update rule stays the same. It's same as the flooding BP, just we are updating variable nodes one by one. The RL agent only decides the update order. The state is built from the local residual mismatch pattern around each can. As I said, when we obtain the W before and W after, we just take a look at the check nodes that are connected to that variable node. So everything is in here is local. I discussed the complexity in detail in the paper, and someone can use it to make it low complexity decoder. And the reward is encouraging the defining W after the updating is encouraging to go to the syndrome that satisfies the error vector that satisfies the syndrome. It means that the delta, we want to seek a delta which is equal to the 0. And as I said, we just take a look at the neighboring check of the variable node. And if an update flips the hard decision at one variable node, only the local checks that are connected to that variable nodes will be updated. This locality makes the scheduling computationally practical. As I said, I don't go to the details, and one can, if want to implement low complexity, can check the paper. The X-only channel that we studied is useful for learning the main idea, but in the depolarizing channel, or even going from the depolarizing channel to the phenomenological channel or from the circuit level noise, it won't be that much hard. It's just generalizing the algorithm. Each qubit in the depolarizing noise can suffer one of the 4 Pauli errors, as I define these 4 2x2 matrices. So now the decoder must handle both bit flip and phase flip simultaneously. This leads to a pair of coupled binary problems instead of only one. Let me go a little deeper. Let's assume that we have this Pauli operator, this error vector Q for act on the n qubits. And for example, take a look at the ith element of this Q vector, Qi. If Qi is X error or Y error, I said that Y error is both X and Z error. If that happens, Qi is one of these. Now we want to map this Q vector of length n to 2 error vectors, X and Ez. Each has length n again, but it's binary now. Each element is a 2x2 matrix. We map each element to a binary element. For example, for Ex, the ith element is 1 if Qi is one of these 2 matrices, and is 0 if it's not. For Z is also similarly, if Qi is either Y or Z and is 0 otherwise. Then when we obtain all the elements of vector Ex, we obtain the syndrome X, and also we obtain the syndrome Z. And in the decoding, we receive this syndrome couple, and from that we want to find Ez and Ex, and then we map it back to the Q. In the depolarizing noise, when we have the error rate of P, it means that with probability 1 minus P, we don't have an error. Qi is the identity matrix. And with probability P, we either have this or Z error. It means that with probability P over 3, we have Qi equal to the matrix X. With probability P over 3, we have Y. And similarly, with probability P over 3, we have Qi equal to the Z. Let's see an example. Assume that we have 12 qubits. Mx is 6 and Mz is 6. So this is our Hx matrix, and this is Hz matrix. And in the CSS, we said that we need to have Hx times Hz transpose equal to 0 mod 2. And in our examples, we just take a look at the CSS code. Assume that this is our Q vector, our error vector, and now we want to obtain Ex and Ez. The first one, we don't have an error, so Ex and Ez both have 0 in that element. The second element is X, So EX, the second element, is 1, but EZ is 0. And whenever we have Y, it means that both of them are 1. If we have Z, just that element of EZ is 1, and element of that EX is 0. And then from these two vectors and from the parity check matrices HZ and HX that I define, we obtain SX and SC like this. So SX is produced by the Z component of the error, and SZ is produced by the X component of the error. Because see, we have this condition. So the HZ transpose, HX times the things that the errors that are produced by the rows of the HZ are detected by HX. So, and a Z error can be detected by HX. And then that if HX times that error is not 0, we will detect it. And vice versa. An X error vector can be detected by HZ matrix. Now, I explained the RL for the X-only channel, and now we want to just generalize it to the depolarizing. It means that having simultaneously X error, bit flip error, phase flip error, or both of them. We define the delta vector for X and for Z, which is the syndrome of the X, XOR by HXE had Z, and also in here SZ plus HZE had X is equal to the delta Z. As I said, the X error is identified by the HZ matrix. And we define the scalar mismatch is the total number of syndromes that are not satisfied. It means the number of ones of delta X vector and the number of ones in the delta Z vector, and we sum them up and it's W. And BIs are the vectors that we define with them the state of our state. Let me go to the Tanner graph, sorry. In here, the BI is the 1, 1, 1s in the syndrome. For example, S6 is 1, this is 1, and this is, for example, 0. We will have, so 1, 1, 0. So that B vector is 1, 1, 0. We obtain it for both the Tanner graph of the HX and also the Tanner graph of HZ. And sometimes if the number of checks that are connected to a variable node is less than 3, the less than the maximum degree, we just pad 0. And in here, the padding 0 is just making it the length, make all the lengths equal to the maximum degree of the variable nodes, and also the Tanner graph corresponding to the HZ matrix. And then we map these binary vectors to the integer values as I explained, and we sum them up to make an integer, a combined integer. For example, if a variable node is connected to 3 checks in the HX matrix and 3 checks in the HZ matrix, in total we will have 6 syndromes that are involved in that variable node. So this integer can become from 0 to 2 to the 6 minus 1, which is 63, and it defines the number of rows of the Q table in our RL, and the number of columns, as I said, it's the number of qubits. And the score that we define is the weight before updating that variable node that we obtain in our RL minus the weight after, divided by the summation of the decrease corresponding for the HX Tanner graph and corresponding to the HZ Tanner graph. And the weights, as I defined in here, is the summation of the syndromes that are not satisfied before and after updating that variable node. And I forgot to mention this. If W after becomes 0, I add a +1 bonus on the score when we are training. Now we go to the results. The first result is on the B1 code. The number of qubits 882 and the number of logical qubits is 24. It means that we encode 24 qubits to 882 physical qubits, and the minimum distance is between 18 to 24. I didn't define what is the minimum distance, but if the minimum distance is higher, it means that we can have hopefully a parity check matrix that will result to a better frame error rate. And in this example, I only considered the X error probability. It means that we only have X error or not having an error. First, I run the BP decoding for at most 100 iteration. And let's see, when the bit flipping is 4%, and when we decode it, the error correction, the FER is also 1, 2, 3, 4, almost 4%. It means that if we have a BP with the budget of 100 iteration and we encode it this much, 24 to 882, and then we bother ourselves with decoding, we don't gain anything when we do the decoding. It means that having encoder and decoder is very useless. But when we go to the 10,000 iterations of the BP, it changes. The performance is in here. When the P of X is 4%, this is almost 1 error out of 10,000. So using the error correction, using QLDPC code, we could improve make the system more reliable, more robust to the errors. But let's go to the sequential decoding on the variable nodes. With just 10 iterations, it means that 10 times we do sequentially order or the variable nodes, we can gain an improved performance compared to the BP with 100 iteration. And when we make it 100 iteration, the sequential variable node, and the order of variable nodes in here are all random, it gets to the 1 over 10,000. And for both BP and our random sequential, they saturate in here. But notice that we get to that saturation point much faster with the sequential variable node scheduling. Now the question is that using reinforcement learning to find out what is the next variable node, can we improve? With just 10 iterations, we get this performance. It already achieves better performance to the random sequential variable node scheduling. And with 100 iteration, we already passed this saturation. And with 10,000 iteration, we get a performance better than the state-of-the-art decoders. BPOSD runs the BP for 100 iterations, and then using solving a linear systems that the complexity is of order of O(n) cube, it gets to this performance. And BPGD, they run the BP, then they decimate the most reliable variable node, then they run another BP, then they decimate the next most probable variable node, etc., until they decimate all the qubits. In here, as the code length is 882, they're using a BP of 100 iteration, then they decimate one, then the 100 iteration, then decimate the next one, and the performance also is in here, and as mentioned in the paper, it saturates in here. So using the RLBP, and where the complexity is on the order of BP, but when we are using OSD, the complexity goes to the order of n cubic, because they are solving a system of linear equations. In this example, I consider B2 code, which is for the depolarizing channel we use, and the number of logical qubits is 48, number of physical qubits is 882, and the minimum distance is 16. And with QBP, we get these two performances, and with our RL, we already have almost one order of magnitude compared to the other state-of-the-art decoders. Then let's have a look at A5 code, which is a smaller code but has a good minimum distance. And similarly, QBP saturates almost in here. The BPGD, they call it quaternary because now we have both X error and Z error, and the decoder is like assuming the LDPC code is a quaternary LDPC code. And when we are using RL, we already get an improvement over the other decoders. Now I compare to the list decoding. It means that instead of just finding the errors for each of the variable nodes that we update, we find one error. But in the list decoding, we assume that, okay, the first error most probably is, for example, X error, but the second most probable error is, for example, Z error or Y error. We consider two of them, X error and the next most probable one, and then using RL, we go to the next variable node, and then we consider both conditions. Now, the first one we had 2, now we have 4, then it branches to 8 situations, and then to the 16. If it becomes more than 8, we prune 8 of them, and we keep just 8 of them. It's a list decoding that is very famous when we are decoding the classical codes, and in this paper, we defined a metric function of how order the different paths, and also we generalized the algorithm for the list decoding, and already we could have a good gain compared to the other state-of-the-art decoders. And note that the latency of the list decoder and the RL that considers only one path, it's very similar if we assume that we can do the list and sorting all in parallel. And it's very possible when the list size is small, we can achieve that. In classical error correcting codes, there are many hardware simulations that they find a very good latency for when we are doing the list decoding. This table, in our simulations, we consider the maximum number of iterations, for example, 1,000, or in here 100. But the average number of iteration can be much smaller. For example, for QBP, when the maximum number of iteration is 1,000, when the when the percentage of the error is 4%, on average we need to just have 2.43 number of iteration. If the error is 10%, the average number of iterations is 166. When we go to the RL, for example, RL, when the maximum number of iteration is 1000, is just less than 2 iterations, we can decode it on average. And when we are using list decoding, even with a small number of iterations, and yeah, so when we go in here, we see that we are using, even though we are updating sequentially, but the overall iteration is much smaller. And note that in our other paper, we use the cluster decoding. It means that instead of updating one variable node at a time, we update a set of variable nodes at a time, and we see that we can again get a similar gain in the error correcting. Then now this block error rate is the same as frame error rate that I defined. It's on the in here it's on the BB code. The 12 logical bits go to the 288 physical bit, and the minimum distance is 18. And similarly, for the QBP, the performance is in here. For the QBPGD, the performance is in here. And note that they saturate almost in here. But with RL, we already passed the saturation point and achieve a very much better performance. And if we are considering list decoding, we'll have already an order of magnitude performance gain in here. And the complexity, as I explained, is in the order of just using the BP. Thank you for your attention and following my work. And as you see, that there are many issues remaining in the decoding, and as I explained, using AI is promising because unlike the classical LDPC codes, the quantum LDPC codes, the Tanner graph has lots of issues, and using AI or considering some properties of the Tanner graph, we can gain a huge gain. And this is a work that we hope that we can even get a further gain in the decoding.